There are a lot of projects related to AI and machine learning that can be done in elementary school. First steps for learning about this is the introduction of concepts that allow kids' understanding to grow, concepts involving intelligence, language, information, data and data visualization, sensors, programming, that sort of thing. So our kids' world will be very, very different from today's world. And let's think about the reasons why kids need to learn about AI and machine learning a bit, at least in elementary school. This image was taken from the top of the world's tallest building, a half-mile high, the Burj Khalifa in Dubai. It's obviously a modern, bustling city, but think of a student entering first grade in 2020, graduating from high school 2032, college entering the workforce 2036. The world will be really different. Of course, self-driving electric cars and robots and intelligent devices every place, maybe the beginning of a Mars colony, warmer climate, and more people. But that misses the point of the impact on everyday life and work, where various kinds of artificial intelligence and machine learning are woven deeply into the fabric of everyday life. So, what do kids really need to learn in elementary school about this? Well, first, how are machines intelligent? How can that be? And how does that compare to human intelligence for kids and grown-ups? And what is this, all this data? Where does it come from? Where does it go? Why is it? And how can we partner with machines? So whether you use technology in an activity or just a discussion, ideas regarding intelligence, both machine and human, are critical. What is intelligence? Where is it? Well, in a human, in the brain, but in a machine, in your phone, where is it? Where's the intelligence of Google? Uh, what are the differences between human and machine intelligence and learning, and the similarities? Uh, so language is a good place to start with young kids because that's a very smooth interface to technology. They don't have to be able to type and spell and all that sort of thing. That's through natural language processing, or NLP. That's something that's made possible through advanced machine learning, where a machine can sound very human and can understand our human language. So uh, historically, humans were the ones who could speak. And even in things like our cartoons, we'd have things like speech bubbles. But way before that, in the Middle Ages, the little scroll that you see above the heads in a medieval painting, that was their equivalent of a speech bubble. That's their speech or thought. But way before that, in 1,000 years ago, in Mexico, in the Mayan and Aztec civilizations, there's a ball player there with a speech scroll coming out of his mouth indicating speech, or the crow underneath him with not only speech symbols, but also the actual words that he is supposed to be saying, if you can read that language. Now, birds, like a gray parrot, actually can speak to Alexa and can listen to what Alexa says, and they can have kind of interesting conversations, I guess, if you're a parrot. Uh, but our digital assistants now can have learned language to a large degree. How well, and do they understand it? Those are good questions for a first grader. Do you have Alexa at home? Does your mom talk to her phone? Does it always understand her? For a child who's learning English, does the device always understand that child? You can say, Alexa, what did I say? To hear what she actually heard you say. So information has been with us in written form for a long time, 4,000 years or more. It's been collected in places like libraries, the Great Library of Alexandria in antiquity to today. This is about a 150-year-old image of the public library in Cincinnati. And whether the words were written or printed on clay or papyrus, bamboo, silk, parchment paper, our world today has left that behind. Everything is digitized, whether it's film or photos photos or music as well as text. And the data, the information isn't stored in libraries as much as in servers, such as the image to the top right. So that's a server farm. That's when we hear about information in the cloud, that's what we mean. It's in the thousands of computers that you can see in that one big room. Where is that room? It's in the basement of that building to the left, the one with the sloped roof. That happens to be the modern Library of Alexandria, Egypt, not too far from the Library of Antiquity. It overlooks the Bay of Alexandria, the harbor of historic interest, where Caesar burned the harbor buildings so that his ships could escape the Egyptian army. Cleopatra's dock from her palace was right there at the bend in that highway. That's where she met Mark Antony when he stepped off his ship from Rome. Uh, Much of our information throughout history has been numeric information, data. So these are ideas that fascinate kids because it's new to them. So that clay disc has cuneiform writing from the Sumerian civilization that actually records the amount of silver in the Sumerian treasury. Under that, with the funny pictures from pre-Columbian Mexico, the images above one another are their language, but their numbers are the colored dots and lines under that. Most of the books in the libraries, and the Aztecs and the Mayas, were not fiction or stories or records of battles. They were records with numbers. They were data. Data and the ability to work with numbers has been so highly prized throughout history that in the 1700s, the educated elite took up something called cursive writing. Where did they get that? They got it from French clerks who used that to write numbers in their ledgers. So here again, data is no longer written, it's digitized. And there's so much of it that we can't understand that many numbers. You can't look at 1,000 or 1,000,000 numbers on a page scrolling by and make any sense of it. It has to be visualized. It might be in a weather map created from the temperature numbers from millions of weather stations or thousands of them. Whether it's a global weather map or to the left, the graph of average yearly temperatures from the year zero, 2,000 years of temperatures. And this graph has convinced millions of people of the imminence of massive climate change. You can see that massive spike toward around the year 2016 is not normal. It's faster and much more, and has greater magnitude than any change from recorded history. It's how we track the spread of viruses, like the Ebola virus map in the middle. And it's the way we make things like brain images. It's not a photograph. That's a reconstruction from millions of bits of data from an MRI scan into an image that makes sense to people. So for kids to learn, Gapminder is one of the best ways to learn how to visualize data. They won't be seeing massive spreadsheets of numbers. They'll be seeing visual graphs of various kinds, and they need to be able to interpret those. Elementary school is a great place to do it. In one day, we collect more data now than maybe in 100 years from colonial times. So this Gapminder graph actually is composed of over 100,000 data points that are actually analyzed and aggregated and displayed in seconds to create this graph. Things like animated graphs, like this graph was an animated graph, are ideal to show change in climate and things like virus spread. Programming is a great thing to begin in elementary school. Some nations, like the United Kingdom, have mandated that this begin in first grade. And the Scratch Junior program is one of the best choices to make. There are lots of other cool systems, but there are reasons why Scratch Junior is great. It's designed for kids from 5 to 8, very roughly. And kids could choose a background for sort of a a digitized animated story that they'll tell. They can select characters. There are 3 in this story. Each character can be programmed from the tiles that you see in that bar in the middle. Uh, and the kids assemble their program by putting the tiles together in that white space at the bottom. Great introduction to programming, and it prepares kids for the full Scratch program. Uh, Scratch and Scratch Junior were created at MIT's Lifelong Kindergarten program, a program whose mantra might be called Deep Learning Can Be Fun, sometimes called Hard Fun. So if you look at that program in the middle, without knowing anything, you can kind of see what it does. I can tell you that it controls something that's moving, like a car or a person or a ball of an animal. When the green flag is clicked, the item, the ball, the car, goes to x equals 0, y equals 0. That's the origin of coordinate axes. So in 3rd grade, kids are learning this. Then it points in direction 135. What's that? Those are degrees. So kids learn that. Then forever it moves 10 steps. If it's on the edge, if it hits the edge, so it's running off the screen, it bounces back and continues. The larger program to its right is actually directly from a 3rd grade Common Core activity. And the braces show the computer science concepts that this is intended to teach. So again, going through this, when the green flag is clicked, first thing is set score to 0. Score is a variable that the student created. Then forever it loops through, change y by -10. Well, y is the vertical axis. -10 is moving down. So there's something that's falling. Think of a ball that's falling. If it touches the paddle, meaning if a ball touches the paddle moving back and forth, the student moving the paddle so that the ball is kind of caught, then move the ball back up to point y equals 180, the top of the screen, and randomly someplace in the x-axis back and forth. So kids are learning positive and negative numbers and the idea of randomization, how important that is in things like a game. Then change score by 1. In other words, I got a point. But if the ball misses the paddle and goes to y's -150, game over, stop everything. So this is what Scratch looks like in its entire environment. This program is very similar to the one just described. In this case, the boy changes his sort of stature, and he moves back and forth. If he hits the ballerina, he turns and moves the other direction. If he's ready to go off screen, he turns and moves back, and it goes back and forth and back and forth. Great preparation for programming of all sorts. So there are loads of choices for activities in elementary school to prepare kids for AI and machine learning. Lots of them are highly engaging. Look at this image with the robot. Every person's eye, every kid's eye is glued to that robot, right? What could be better? Well, the kids are engaged in the activity. Are they engaged in the content? What's the content? Well, if it's AI, the content is intelligence. How smart is that robot? What can it do? Do they know that? If it's machine learning, that's about learning. How can a robot learn? How does it learn? What can it learn? Do the students get a chance to teach the robot anything? Do the students get a chance to control the robot? Looks like there's only one robot, but lots of kids. How much activity does each student have in that learning? It's lots of fun. Is it meaningful? So just to review, the kinds of concepts that kids can talk about in discussion or can actually actively work with and hands-on relate to intelligence and language, data and visualization, programming, and how this may change their own future life and jobs. Big idea is this isn't like a drop that falls into sand and disappears forever. This is more like a drop that falls into a calm lake, creating ripples that expand forever through the child's brain and possibly throughout their life.